Hello TNA, and welcome to lesson 2 of your energy topic in science. Last lesson we talked about the different types of energy stores and how we can transfer one store to the other. Today we're going to look specifically at elastic potential energy and the elastic potential energy store and how to calculate how much energy is stored there. So for this lesson you will need your paper or your booklet, whatever you're working in. You'll need your regular colored pen for your notes and annotations, your feedback color pen for when we do questions, and we will need a calculator for this lesson. So if you have a scientific calculator at home, grabbing that, putting your phone away, otherwise putting your phone on do not disturb mode and making sure that you have a scientific calculator available on your phone, whether that be just in the calculator app or if you download a different calculator for that. So now that you have all of that ready to go, I'd like you to have a look here, give this knowledge check a go, writing down your answers on your paper, and then coming back, replaying the video for the answers in a moment. Now we'll go over the answers from your knowledge check. Hopefully you remember from previous lessons that a scalar quantity or a scalar number has only magnitude. And you'll remember that magnitude is just a fancy science word for size. Whereas a vector quantity has magnitude or size and direction. If you had forgotten this, making sure you make a note of it now on your page, that a scalar has only magnitude and a vector is magnitude and direction. Because energy doesn't have a direction associated with it, it's only a size, we know that energy is a scalar quantity. The unit for energy is the joule, which is represented by a capital J, but please make sure that you do have the word joule written down. Its stretched elastic band has the elastic energy store. A moving object has energy in the kinetic energy store. A pathway which moves force through a distance is the mechanical pathway. The other three pathways we have radiation, heating, and electrical. The energy store that starts with C is the chemical, and G is the gravitational potential. Remember that you do need the potential for that type of energy, and the unit for mass is the kilogram. Or kg. So making sure you have those correct answers written in, and we'll move on to the lesson. So today we're going to talk about elastic potential energy. Now before we get going into it, I want to clarify what the word potential means, because we've talked about it for gravitational potential energy, but elastic potential energy is also a type of potential energy. So any energy that's stored has the potential to do something, but it's not currently doing something. So the same for elastic potential energy. If you've stretched an elastic band, for example, it can do something and it has the potential to do something, but it's not doing something at that minute until you let it go and release that energy. So elastic potential energy, potential means the ability to do something, but not doing it actively. So it's the same kind of idea as when a teacher says that a student might have potential. They have the ability to do something, but they're not actively doing it at that minute. All right, so elastic potential energy is, remembering from last lesson, the energy stored in something that's been stretched or compressed. And compressed is the scientific word for something that's been squeezed. So for example, if you squeeze a stress ball, it will go back to its original size, and that has some energy you've put into that. So elastic potential energy is often called strain energy, as it's energy stored in a stretched object or an object under strain. So it's energy stored in a stretched object, or, as we've just said, a stretched or compressed. All right, so the typical example is a stretched spring or a stretched elastic band. Stretching a spring requires a force. So in order to get that string stretched, we need to exert a force. So the pathway to transfer the energy will always be mechanical energy, because we need to put a force through a distance. You may recall work is done whenever energy is transferred using a force. So that energy is transferred. So when we move from the energy in your muscles into the stored energy in the spring, we call that work. In a stretch spring, the energy stored is equal to the work done to stretch the spring. All right, we can't make energy from nothing. The work done is the same as the energy. So those two values are always the same. This value can be calculated using this equation. Elastic potential energy equals 0.5 or 1/2 times the spring constant times extension squared. So this is an equation that will be given to you on your physics equation sheet, but you do need to be familiar in how to use it. All right, because it will only be given to you as the symbols like this. So you need to know what those symbols mean. So the EE, so the big E is for energy. The small e is for the fact that it is elastic energy. So the elastic potential energy. 1/2, we know from maths that to put 1/2 into a decimal is the same as 0.5. So when you put 1/2 into your calculator, 1/2 is the same as 0.5. So that's how you can do that. The K is the spring constant. So K is what we call the spring constant. And it is how stretchy a spring is. So how easy it is to stretch or compress the object. Again, usually a spring, but it could be an elastic band, it could be anything else, and it's how easy it is to stretch, because you know some bands are very easy to stretch and some you have to put a lot more force in to stretch at the same amount. And then E stands for the extension. An extension is how much it has been stretched. Now, because of the way that science works, we always work in what we call SI units. So SI is a French term, but it means the scientific. So SI unit is the scientific unit. So for example, when someone asks, how much do you weigh? You normally, in everyday terms, talk about stone. But stone is not the scientific term for how much you weigh. Weight, you might remember, is a force. So you would talk about how many newtons you weigh or how many kilograms your mass. So the SI unit for mass, for example, is kilograms. If we want to talk about something in grams, we have to convert those grams to kilograms to put it into an equation. All right. So the same way for length, how much it has stretched, it's a length and you can sometimes talk about length in everyday terms in inches or feet or miles. The SI unit, so the unit we have to use in science class for length or extension or anything else, is meters. Sometimes if you're measuring it and it's only a little bit, you might measure it in centimeters, but to plug it into the equation, you always have to convert it to meters. So for the SI unit for length is meters. So the elastic potential energy is a form of energy. So the energy is always in joules. And the spring constant our SI unit is newtons per meter. So newtons per meter. Remember in science that the slash means per, that we read that as per. So spring constant, newtons per meter. Our energy is measured in joules and our extension is measured in meters. When you're saying it out loud, you need to make sure that you are saying the full word and not just the letters. And I want you to be saying the full words in your head as well to get used to what do those letters mean. Because the letters on their own aren't helpful. So energy, EE, is measured in joules, which the symbol for is J. The spring constant, which is K, is measured in newtons per meter. An extension, which is E, is measured in meters. So you need to make sure that you keep clear in your head the difference between a value versus a unit. So the value is what we are measuring. So that's the energy, that's the spring constant, that's the extension, versus the unit is what we're measuring it in. Is it measured in kilograms? Is it measured in joules? Is it measured in newtons per meter? So the value versus the unit. So now I'd like you to give this checkpoint here a try. What is the equation for elastic potential energy? Give SI units for all the quantities involved. Answer the question without looking back, and I'll go over the answer in a moment. So in your feedback color pen, I want you to double check what you have written down. So you should have elastic potential energy. Remember, when we're saying it, we're not saying EE. You can write down the things, but I want you thinking elastic potential energy equals 1/2 or 0.5 times our spring constant times our extension squared. So that's the equation. The SI units for all quantities involved. So elastic potential energy, our SI unit is joules. Our spring constant, our SI unit is newtons per meter. And our extension, our unit is meters, because it is a length. So when we're doing a maths question like this on a physics exam, and remember your physics exam is 30% maths questions like this, which is really scary at first, but they're actually the easiest questions to do, because they're usually worth about 3 or 4 marks each. And it's always the same steps you need to do. And as long as you go through the steps, they're quite easy to get all the marks for. So I want you to make sure that you're going through all the steps as you're doing it, because then even if you punch something wrong in a calculator, you only lose out on 1 mark instead of losing out on 3 marks. And it happens more often than you think. So the worked example, an ideal spring whose spring constant is 14 newtons per meter. It's stretched 0.40 meters when a mass of 0.560 kilograms is hung from it. How much elastic potential energy is stored in the spring? So we're looking at the question. We see how much elastic potential energy. So we know we need the equation for elastic potential energy. So your first step is to figure out which equation you need and to write down the equation. That's always 1 mark. If you can pick the correct equation, it's 1 mark. So always just write that down, and it's not even pulling anything out. Then you need to plug in your values. So we have 1/2 is 0.5. You can leave it as 1/2 or you can put it as 0.5. That's fine. Our spring constant, we look into our formula, or we look into our question, 14.0, so 14, and our extension stretched by, that's our extension, is 0.4 meters. So you plug that in. We haven't used the mass, but it's not part of the equation, so we don't need to use the mass. So sometimes they'll give you something else to try to throw you off, but you don't need to be thrown off by that because you know that the mass is there. And then the third step, the third mark, is to plug those numbers into a calculator and end up with 1.12 joules. Something you need to remember here is your bid mass. So you need to remember to do your squared before you multiply. So your index is before your multiplication, so you need to square it before you multiply. So you need to make sure that you do that and often not all your calculators will do bid mass for you automatically. So the way I would punch this into my calculator, I do 0.4 squared times 14 times 0.5, which will give you the answer of 1.12 joules. I would like you to give that a try. Plug that into the calculator you have now to make sure that you're plugging it in correctly and getting to that correct value. All right, so now we're going to try this next one. So question 1, a spring with a spring constant of 120 newtons per meter. So I'm going to highlight that because I know that is stretches by 0.02 meters. So we have our spring constant. So we know that's our K is our spring constant. And we see the units, newtons per meter, that's fine. Stretches, how much it stretches by is our extension. So 0.2, that's in meters again, that's fine. What is the elastic potential energy of the spring? So that's what it's asking, that's the third value. So my elastic potential energy, so I know, step 1, write down my formula. Elastic potential energy equals 1/2 times spring constant times extension squared. So step 1, done, 1 mark. Step 2, plug in my values. My elastic potential energy, I don't know that. That has been given to me, so I just write that down. Equals 1/2, that's a number, times my spring constant, 120, it's in newtons per meter, times 0.02 squared. All right, you can write this as 0.5 if you like, to make that easier for you to remember. So that's my formula there. Then now I have to plug that into my calculator. So you go to your calculator, you type in 0.02 squared, and then you multiply that by 120 and multiply that by 0.5, and you end up with the number of your elastic potential energy equals 0.024. That's not going to get you the mark. You need to include the unit. The unit for energy is joules, so 0.024 joules. There's your third mark. So now I'd like you to give a go to question 2. Pause the video, do question 2, and then we'll go over the answer in a moment. So now we'll have the answer. So what you should have done is gone through the question. Spring constant of 200 newtons per meter. Again, meters, newtons per meter were fine. 0.3 meters. The elastic potential energy is what we're looking for. And so we have step 1, always write down your formula. Elastic potential energy equals to 1/2 times spring constant times extension squared. There's your first mark. Even if you plug it wrong into your calculator, if you've written that down, so you should have it written down in your books now, you will get the mark for that. Step 2, plug your numbers into the equation. So elastic potential energy, we're not given that. Elastic potential energy is equal to 0.5 or 1/2 times our spring constant, which is 200, times our 0.03 squared. So you plug all of those into your calculator and you should end up with a value of, so your elastic potential energy, you end up with a value of 0.09. Again, you need your unit of joules. So even if you don't have a calculator, even if you can't remember what to do, step 1 and 2 is writing down the formula, plugging in the numbers. You can always do that. There's your first 2 marks already. Regardless if you don't know what to do, and then plugging numbers into a calculator is simple enough. There's 3 marks. Don't let the maths question scare you. So for the next question, again, doing the same thing. Pausing the video, giving that third question a go, and then we'll go over the answers in a moment. So question 3, again, start with highlighting what you know. So how much energy, that's what we're looking for, is stored in a spring. So we know it's elastic potential energy because we're talking about a spring with a spring constant of 150 newtons per meter. We don't have to convert that. Compressed by 0.02 meters. Again, meters already in the right unit. So next thing we do, we write down our formula. So our elastic potential energy is equal to 1/2 times our spring constant times our extension squared. So next thing we do, plug in our values. Elastic potential energy equals 0.5 times our spring constant of 150 times our times our extension by 0.02 squared. We plug that into our calculator, again, starting with the with the extension for bid mass, and we end up with the value. Our elastic potential energy is equal to 0.03 joules. So looking at the next page, there are several questions here. I would like you to pause the video, and if you feel okay with it, you can just go through and do all these questions 4 through 8. If not, pause the video, watch the answers for question 4, and then pause the video, try question 5, then watch the answer for question 5, pause the video, try question 6. Once you feel you can do it on your own, just try the rest of the questions and come back and rewatch the answers afterwards. So answers for question 4. Spring with a spring constant of 10 newtons per meter stretches by 2 meters. We know that's our extension. What is the elastic potential energy of the spring? So again, we know 2 meters is our extension. This is our spring constant. So our elastic potential energy is equal to 1/2 times spring constant times extension squared. So our elastic potential energy is equal to 0.5 times our 10 newtons per meter times 2 meters squared. So we plug 2 meters, so 2 squared times 10 times 0.5 into your calculator. You end up with an elastic potential energy of 20 joules. So again, your 3 marks. Answers for question 5. We have, again, spring constant 20 newtons per meter, 3 meters. What is the elastic potential energy of the spring? So we know our elastic potential energy is equal to 1/2 times spring constant times our extension squared. Our elastic potential energy is our unknown. 1/2 is 0.5. Our spring constant is 20 and it is newtons per meter, so we're okay. Our extension is 3 meters squared. So our stretches, it's the amount it stretches, we know that's our extension. We plug those numbers into our calculator, so 3 squared times 20 times 0.5. We end up with a value of 90 joules. Again, if you forget the joules, you didn't get the correct answer. So how much energy is stored in a spring with a spring constant of 160 newtons per meter when it's compressed by 0.04 meters? Pause the video, give it a go. Our answers, we start with writing our formula. So our elastic potential energy is 1/2 times our spring constant times our extension squared. Our elastic potential energy is equal to 1/2 or 0.5 times our spring constant is 160 newtons per meter. So we're all right there, times our extension, because it's compressed, which means it's gotten smaller. So, but again, the overall amount it's been compressed or stretched by doesn't matter. 0.04 meters squared. So you plug that into your calculator. 0.04 squared times 160 times 0.5. Our elastic potential energy is equal to 0.128 joules. Again, don't forget the joules, otherwise you won't get that final mark. But you've already gotten 2 out of 3 marks, even if that is the case. So spring with a spring constant, K, this one gives it to you nice and easy. K, 0.75, stretched, so we know this is our extension. What is the potential energy now stored in the spring? So it's changing the wording a little bit, but it's still asking the exact same thing. The potential energy stored in the spring, so we know it's our elastic potential energy, and we know that's 1/2 times our spring constant times our extension squared. So our elastic potential energy is equal to 0.5, this is how you'd plug it into a calculator, times K, our spring constant, 7.5 newtons per meter, times our extension of 0.40 squared. So our elastic potential energy is equal to, you plug that into our calculator, 0.4 times 0.4 or 0.4 squared times 7.5 times 0.5, and we end up with the answer of 0.6 joules. So this one looks a little confusing, but again, if you go straight into the question and go, graph shows the extension for a stretch spring constant. So I have my spring constant of 200 newtons per meter. Calculate the amount of energy. So we're looking for our elastic potential energy stored in the spring when it's stretched by 700 millimeters. So this is our extension. Those are the values we need. We don't actually need to look at the graph. The one thing you do need to be careful of here, 70 millimeters, we have millimeters, we don't have meters. So we need to convert millimeters to meters by dividing the value by 1,000. So our extension is 70 millimeters, which when we divide that by 1,000 is equal to 0.07 meters. So now we do all the same steps. We have an elastic potential energy is 1/2 times our times our spring constant times our extension squared. So our elastic potential energy, we don't know that. 1/2 is the same as 0.5. We know our spring constant, 200 newtons per meter times 0.07 squared. And again, now we're just going back to the same steps. Plug that into your calculator. Our elastic potential energy is equal to 0.49 joules. So here are the answers for questions 4 through 8. Making sure you have those in. If you're feeling okay about them, continuing on question 9 and 10. If you're still struggling a little bit, give question 9 a go. What's the answer? And then we'll go do question 10 together. Question 9. So this one started getting a little bit more tricky. But again, if you just look for the values you need and plug the numbers into the formula, you'll always be able to do these questions. So truck spring has a spring constant of 5.0 times 10 to the 4 newtons per meter. Now, most calculators won't let you plug it in that scientific notation, so we need to put that into standard form. So in order to do that, hopefully you remember, so our spring constant is equal to 5.0 times 10 to the 4. Now, because 4 here is a positive number, I know my number is getting bigger. So that's 5, and I move that decimal point over 4 spaces. 1, 2, 3, 4. Add my comma there, so it's 50,000 newtons per meter. And I can plug that number into a calculator all the time. So 50,000. When it's unloaded, the truck sits 8 meters, 0.8 meters above the road. When it is loaded with goods, it lowers 0.7 meters above the ground. So we can't take either of these two numbers as our extension, because remember, extension is how much it has stretched or compressed. So that extension is the difference between 0.7 and 0.8. So our extension is equal to 0.8 subtract 0.7, which is 0.1 meters. So that's our extension. How much potential energy is stored in the 4 springs? So how much potential energy? We know that's elastic potential energy because we're talking about springs. So just back to our equation. Elastic potential energy is 1/2 times our spring constant times our extension squared. So, and now we have those numbers, we can just plug them in. It makes it a lot easier, a question like this, that if it's not directly in the question, just writing down your values just like this, because then you know you can just plug them in, and this is worth here. This is worth a mark on its own. Being able to convert and figure out those values, those are each worth a mark. So it's 0.5 times our spring constant times 50,000 times our extension, 0.1 squared. Now it's just a case of plug it into a calculator. So 0.1 squared times 50,000 times 0.5, we end up with an answer of 250 joules. Now, question 10. Pause the video, give it a go, and I'll be here with the answers in a minute. So the first thing always, spring constant, 500 newtons per meter, extends back by 0.6 meters. So here again, this is our extension. They sometimes use different words, but just think about what is extension. It's how much it has stretched or compressed. So pulls back, calculate the stored potential energy. Stored potential energy in the bow. So same as we always do. Elastic potential energy equals 1/2 times our spring constant times our extension squared. So our elastic potential energy is equal to 0.5 times our spring constant is 500 newtons per meter times our extension, 0.6 meters. Simple, we don't need to convert anything. Meters, don't forget the squared. Plug that into our calculator. Elastic potential energy. So 0.6 squared times 500 times 0.5, we end up with 90 joules. So now that we've looked at how to just use the basic formula, you also need to know what happens if you're given the elastic potential energy, but you're missing something else in the equation. The same we start doing it the exact same way. So an elastic spring stores 45 joules of elastic potential energy. So we have our 45 joules. We know that this is our elastic potential energy when it is stretched by 2 centimeters. So we know it's stretched by a length. We know that is our extension. We see here it is 2 centimeters, so we need to convert that to meters. So to convert centimeters to meters, divide the length value by 100. So we go 2 divided by 100 is equal to 0.02. So we know our E is equal to 0.02. What is the spring constant, which is represented by K? And so that's what we need to figure out. The easiest way to do this is doing it the exact same steps, the exact same way. So we figured out what we need. We know we have our elastic potential energy, extension, and spring constant. So we write down our formula, which includes those things. So our elastic potential energy is equal to 1/2 times our spring constant times our extension squared. We know that. And then, again, we plug in the values we know. We know our elastic potential energy is 45. Not 1/2 is the same as 0.5. We don't know our spring constant, so we just simply write the letter. And we know our extension, 0.02 squared. So you can take your 0.02 squared and figure that out now, is the easiest way to do it. So we know 45 is equal to 0.5 times K times, changing that into just a regular number, and it does turn into 0.004. And then we just have to move the 0.5 and the 0.004 to the other side. We look at our multiplication. We know the opposite of that is dividing. So we just have to divide those from the other side. So we end up going 45 divided by 0.5 divided by 0.004. You plug that in, is equal to K. We can plug that into our calculator and we end up with a value of K is equal to 225,000. Then we need our units. We know our units for our spring constant are newtons per meter. So you just do it that exact same way, plug it into the calculator the exact same way, and you end up with the same numbers. So question 2, we'll do it one more together and then you'll have a chance to do some on your own. So a spring stores 68 joules of elastic potential energy when it's stretched by 6 centimeters. Again, centimeters we have to convert to meters. So 6 divided by 100 equals 0.06 meters is our extension. We have our elastic potential energy. Spring constant is our unknown, is what we're looking for. So we start with, that's right, writing down the equation. So elastic potential energy is equal to 1/2 times our spring constant times our extension squared. And then we plug in the numbers. We know our elastic potential energy is 68 joules times 0.5 times K times our spring constant, which is unknown, times our extension, which is 0.06 squared. And then we need to get our K on its own. We need to isolate for K is another way to describe it. So we just move everything else to the other side. So 68 divided by 0.5 divided by 0.06 squared is equal to K. We can then just put this into our calculator and end up with a value of K is equal to 37,777, repeating. Don't forget the unit of newtons per meter. That is a 4-mark question. The only science you need to be able to do is to remember that this is the formula you need. Everything else is simply plugging in numbers. So I'd like you to give a go to question 3 on your own. We'll go over the answers in a minute, but you just need to give it a go. If you get stuck, you can watch the answers. So looking at question 3, we have our 89 joules of energy stretched by 5 centimeters. We have to be careful that centimeters, we need to change it to meters. So it would be 0.05 meters. And our spring constant K is our unknown. So we write down our equation of elastic potential energy is 1/2 times our spring constant times our extension squared. We have 96 is equal to 0.5. We're just plugging in the numbers times our spring constant and our extension 0.05 squared. Then we need to rearrange to get K by itself. So it's just 96. Again, because we're multiplying, we just need to divide. Divided by 0.5, divided by 0.00, divided by 0.05 squared is equal to our spring constant. So our spring constant is equal to, once you plug those numbers into a calculator, remembering your bid mass, we end up with 76,800 newtons per meter. Now give 4 a go on your own. Well done, you've unpaused the video now. So we have our 10 joules of elastic potential energy stretched by 2 centimeters. What is the spring constant? Looking again, we have our centimeters. So converting our 2 to 0.02 meters. And then we do the same steps again. Write down our equation. So elastic potential energy equals to 1/2 times our spring constant times our extension squared. This step might seem a bit much now. But if you forget to convert here, forget to do this conversion, you might miss all the marks if you haven't written down the equation. If you write down your equation, you already have 1 mark. So it's a very simple mark to have that you don't want to make a silly mistake or punch a number wrong into a calculator and simply write down the answer and get no marks for a rounding error or for a decimal point error or something like that in your calculator. All right? Because we're not testing, can you use a calculator? We're testing, can you work through the problem? So plugging in the numbers now, we have 10 is equal to 0.5 times our spring constant times 0.02 squared. So to get that K on its own, to get that spring constant on its own, 10 divided by 0.5 divided by 0.02 squared, and then is equal to our spring constant. You plug that into your calculator. So our spring constant is equal to 50,000 newtons per meter. Now, if you are looking carefully, you know that we can convert this into scientific notation. So we can look, here's my decimal point. I can move it 1, 2, 3, 4 places. So I can go K is equal to 5.0 times 10 to the 4. Because this is a big number, it's a positive 4 newtons per meter. That would be your extra step, and get used to practicing like that so that you can write the numbers like that, because sometimes it gets a lot easier. So I'd like you to give question 5 and 6 a go on your own, and we'll go over the answers again in a minute. So question 5, we have our 30 joules of elastic potential energy stretched by 10 centimeters. Centimeters, we need to convert that to meters, so it's 0.1 meters. What is the spring constant is K is what we're looking for. So we write down our equation. Elastic potential energy is equal to 1/2 times our spring constant times our extension squared. We have our 30 joules is equal to 0.5 times our spring constant times our 0.1 squared. And so then we go, our spring constant is equal to 30 divided by 0.5 divided by 0.1 squared. So we know our spring constant, once we plug that into a calculator, is equal to 6,000 newtons per meter, or it's equal to 6.0 times 10 to the 3 newtons per meter. And question 6, again, start with what you know. We know there's 68 joules of potential energy when it starts by 5 centimeters. 5 centimeters we have to convert to meters. So 5 divided by 100 is 0.05 meters, which is our extension. What is our spring constant? Our spring constant is our unknown, is our question mark. So our elastic potential energy is equal to 1/2 times our spring constant times our extension squared. So we have our 78 is equal to 0.5 times our spring constant times our 0.05 squared. So then we go K is equal to, our spring constant is equal to 78 divided by 0.5 divided by 0.05 squared. Plug all those numbers into a calculator and you end up with a spring constant of 62,400 newtons per meter. If you are struggling with this, make sure you go and ask your teacher about it. They can re-explain it to you, they can explain it to you in a different way, but you do need to make sure you know how to rearrange the formulas and plug the numbers in. We will be looking at lots more formulas this topic of different equations of plugging numbers into it, so you need to make sure that you are able to do this. So if you're struggling now, catch up and get to it. So here are some more questions doing the exact same thing. So if you have a good handle on it, just give these questions a go. If not, we'll do the first one together and then watching for the rest. So we start the same way we do any other one. You highlight or you write down the things we know. So we have a spring constant of 60 newtons per meter. We have 24 joules of elastic potential energy. How much is it compressed? So we know our spring constant. Spring constant we have is K. This is our elastic potential energy. How much is it compressed is our question. So our E, our extension, is what we don't know. So again, write down our equation. We have elastic potential energy in our question. We have 1/2 times we have a spring constant and we have an extension. It's asking us for the extension. Plug in the numbers that we know. So we know we have 24 joules of elastic potential energy is equal to 0.5 times a spring constant of 60 times our extension squared. So it's all multiplied. So in order to move the other two, we need to move them to the other side. So we end up with 24 divided by 0.5 divided by 60 is equal to our extension squared. In order to figure out just the extension, we need to do the opposite of squaring, which is taking the square root. So our extension is the square root of everything here. So the square root of 24 divided by 0.5 divided by 60. If you feel more comfortable, you can calculate what this number is equals to x, for example, just equals whatever number it is, and then just take the square root of that number is also fine. So once you plug all of this into a calculator, you end up with an extension of 0.89 meters. You may need to do some rounding, especially when we're dealing with square roots. So rounding to 2 decimal places is usually what we look for. So now giving question 2, 3, 4 a go, using the examples, we'll go over the answers in a bit. And here are the correct answers for the last couple questions. Making sure that you are rounding it as you need to be. So for example, question 2, this, when you punch it into your calculator, it's not 0.478 dot 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 dot. But if we're rounding it to 2 decimal places, then we need to look to the right of that 7. It was an 8, so round it up because it's greater than 5. So this is why you're taught those rounding and those things in your maths classes, so you can apply them into your science classes. Now, there's a table here that's an extension. So this one needs to be your elastic potential energy with your spring constant and your extension. So filling out this chart and sending it to your teacher as your extension activity. If you have any questions about any of this, remember you can always email your teacher your questions, or you can look online, BBC Bite Size, and everything else has lots of great resources on it as well. We will be doing lots more questions like this, but you do need to make sure that you know how to do these maths questions. Don't forget to do any other assignments that your teacher has set for you, and have a wonderful day.